Hello there, and welcome to my lesson on logistic growth. This is going to be a BC calculus topic. It's going to be something related to differential equations and slope fields. And what we're going to be looking at in this lesson is, first of all, explaining what a logistic growth function is going to be, what it's kind of used for, and then we're going to see how do we maybe take the differential equation to create a general solution that we could actually make a little bit more sense of rather than having the differential equation that just gives slope values and go from there. Here, what it's telling you is that it's saying that there's four basic differential equations that you need to be able to understand what they are. The first one is position, velocity, and acceleration, which is something that we cover early on, kind of in AB calculus, where we can say that the acceleration function is the derivative of the velocity, and therefore it's going to show us what the acceleration due to gravity is going to be. The specific solution would just be negative gt plus c, and c in that particular case would typically represent, not a position, not a starting position. It's not gonna, maybe something more along the lines of what an initial velocity is going to be. The second one is simple growth and decay. Now the simple growth and decay function, what you're seeing here on this screen or on the board, most people are familiar with it like this, where it says y is equal to c times e to the kt power. Sometimes they see it as, I don't know why my marker is so thick here. I don't like it that thick. Sometimes you see it as like y will be equal to a times e to the kt power. Sometimes you see it like as y is equal to maybe like p naught or something like that, e to the kt power. That first value, ca p naught, they're really just talking about an initial value that you start off with. But those are two types of differential equations that you probably have seen previously. The third one that we're going to be looking at is going to be a logistic growth function, and the growth could be upwards or downwards depending on what the situation is, the values that you're getting. Here, the differential equation for exponential growth is an assumption that it's going to go forever. So on that last example that we saw, that y is equal to e to the kt power, or c times e to the kt power, I should say. Those are things that you may have even seen, like in not calculus, but chemistry classes. I know I've used problems like that in earlier algebra classes, because it does represent, a good growth model over a certain period of time. The thing is that growth cannot be unbounded. There's going to be a limited resources of some kind that's going to limit a population growth. Here, like they're talking about an epidemic outbreak, if I could get my mouth to work properly. We talk about like, zombie outbreaks and all that stuff. And if there's going to be an outbreak of any kind, whether it's a viral outbreak, cells that are growing in a petri dish, or even sales at, or new items that are going to be for sale at a store. Places like Walmart like to use logistic growth functions to know when something should go on sale. But that's what they're going to represent. They're going to show you kind of the exponential growth that you see initially, but it's also going to show you a logistic or a logarithmic, I should say, curve as it kind of slows down when it reaches its upper limits. Now, the growth that it gets to, the highest it'll wind up being able to grow, That's referred to as the carrying capacity or the limiting factor, which they call L. Okay. Now, most real-world situations do not grow without bound. Naturally, there's only so many resources in the world to produce, like, I don't know, bunny rabbits or something in a given environment. But what we see here is the logistic growth equation, where they're giving us dp over dt is equal to k times p, where p is going to represent the population of something or the amount of something. L is going to represent the limiting factor, and K, and I think I neglected to mention it, I know I have it written down, but K, whether it is in this general simple growth formula, represents the relative growth rate, whether it's increasing or decreasing. It'll be the same thing here. K is going to represent a relative growth rate. And what we see is they're giving us in the middle column the differential equation, and on the right side, they're giving us the general solution of the differential equation. Now, in this case, the A value would be representing the C value from like our constant of integration whenever we have to do whenever we would have to do our integration to find what the general solutions are going to be. Now, this is where I'm going to encourage you, those of you that are following along with the notes provided for this class, you may want to give yourself even a blank sheet of paper. I know that the notes are giving you kind of almost like a quarter sheet of paper. You may want to give yourself a little bit more space than that, especially if you write large. If you just happen to come across this video and you're just, you know, working stuff out on your own just to try and get some help with logistic growth stuff, then what we're doing in this example is we're going to show you how we got the general solution to begin with, and it's going to take up a little bit of space. So uh, now that I'm thinking about it, I want to go ahead and give myself some space. So let's see, let's see, can I add a new page here? Sure I can, there we go. Okay, so let's take this, see if it'll let me grab this guy here. And we'll copy that, and then we'll go to a blank, maybe, oh, nope. Oh, hey, that's not, I don't know why that is there. Okay, let me pause for a second and try doing it from my keyboard. One moment. Okay, so there is the general differential equation. dp dt is equal to kp, and in parentheses multiplied by 1 minus p over L. Now I'm going to work this problem out for you, and be patient. It is going to take a little bit of work, and I'm intentionally going to do something that I think a lot of students may do as a mistake just to illustrate, that it's okay to make that mistake. You can always go back and kind of reevaluate things. So the nice thing about this is that it is, a separable differential equation. dB/dt is not a fraction in the traditional sense. However, we can kind of work with it like it's a fraction. We can multiply both sides by dt, and we'll wind up with, oh, turn my pen back on. We'll wind up with dp to be equal to k times p, and in parentheses 1 minus p over L times dt. So essentially what we want to do is we want to get all of the p terms also on the left side of the equal sign, so that way all the p terms are on the same side with dp. So we're going to divide both sides by p and the stuff in parentheses, or multiply by the reciprocal. So we can say like 1 over p times 1 minus p over L dp will be equal to k dt. So now we've separated the differential equation, and at this point what we do is we are going to integrate both sides so that way we can find out what its general solution is going to be. So this is where I'm intentionally going to do something that I think most students would probably try to do on their own, working a problem like this out. And I'm going to, at some point, run into a problem that's going to make it something that's not really going to work well. Okay, so if you don't feel like writing this part down, I get it, but just at least follow along with what I'm doing. Okay, so what I'm going to do is, recognizing here on the left side, let me pick a different color. What I'm going to do is I'm going to focus on this left side here first. And looking at the fraction that we have, that one's not going to be something that I can integrate unless I do, you know, not partial fraction decomposition, but separation by parts. Maybe I am thinking about partial fractions. Yeah, that's exactly what I am. Partial fractions. Sorry, it's been a long day. So I'm looking at 1 over P times 1 minus P over L, to be equal to A over P plus B over 1 minus P over L. So if we try to simplify that expression with a common, a common denominator, we're going to end up with, multiplying everything by P times 1 over P minus L. We're going to end up with a 1 here being equal to A times 1 minus P over L plus B times P. And what we can do at that point is we can try to, figure out what the values of A and P are going to be. So here, if I wanted to find out the value of A, I would make P equal to 0. So let's make P equal to 0, so that way we can find A. And if I make P is equal to 0, the BP term doesn't matter. 0 over L is just going to be 0, so I'm left with 1 is equal to A when I try and find P, or set P equal to 0. That's how we find the value of A. Well, now let's find the value of B, or attempt to find the value of B. And this is where we need to be able to eliminate the A value. So the only way that I can eliminate the A value in this case is if I look at it and I say, well, let's make P equal to L. If I make P equal to L, that's going to give me 1 equals A, and in parentheses, we're going to have 1 minus L over L plus B times L. So this simplifies to be 1, giving me 0 in the parentheses, making this whole thing equal to 0. But I wind up with 1 is equal to B times L, and that would mean that 1 over L is equal to B. And this is where hopefully you're going to start scratching your head and say, well, that doesn't look like anything that I've seen before. And it probably shouldn't. And that's fine. If you wind up working your way through a problem like this and you get to this point, I want you to understand, it doesn't necessarily mean that you've done something wrong. It just means that maybe there's a cleaner way that we can work the problem out. Okay? So let's go ahead and let's go back to what we have here. Let's go back to this part here. And what I'm going to do is I'm going to multiply, not by 100. What am I doing? By L. I'm going to multiply by the denominator L here, and I'm going to multiply by the denominator L here to keep the proportionality of the ratio. And when we do, we're only going to in the denominator, we're only going to multiply into the parentheses, because otherwise you're going to wind up multiplying by L too many times. And what we're going to end up with, and I'll kind of start using the blank space up here on the right, we're going to wind up with an L over, and in the parentheses, what we're going to end up with, we'll end up with P times L minus P. to be equal to A over P plus B over L minus P. And now we're going to try to repeat the process to identify our A and B values. So again, when we multiply with a common denominator, we're going to wind up with L is equal to A times L minus P plus B times P again. So one more time, let's try to get the A value and the B value. So again, to find the A value, I want to set P is equal to 0. So if I set P is equal to 0, again, we're going to wind up with L being equal to A times L. So we divide both sides by L, and I get A is equal to 1, which kind of matched what we were doing before. So that's great. At least we had that kind of confirmation. Well, now let's go and find B. If I want to find B, in this case, we need L to go, or the A term to go away. So in this case, I want P to be equal to L again. Okay? But now when I do my substitution, unless I missed something the first go around, now when I do my substitution, I'm going to wind up with L equals A times L minus L plus BP. Nope, B times L, because we're saying P is equal to L. Well, you can see inside the parentheses that creates 0, so 0 times A is just 0. So I'm left with L equals B times L, and again I'm going to get 1 to equal to B when I divide both sides by L. So now we have the two pieces that we need for our partial fractions. And now we can kind of keep working from here. So, like I said, I think like if I just gave a kid this particular problem and told them to do separation by partial fractions, I think that this is what they would try to do first, and they're going to wind up with something that's going to be really not fun to work with. So that's why we're going back to the original integration after we did our separation by parts and multiplied both the top and the bottom, in this case by L, to give us something that's going to work out a little bit nicer for us. So like I said, even without doing that extra step, we need some space. So now what I'm going to do is I'm going to just clean this up a little bit. Let's take all of this and make it go away. So now what we have, going back to the problem that we're trying to solve, we have the integration. In this case, it's going to be 1 over P plus 1 over, nope, said 1 and I wrote a P. 1 over, what did we have? L minus P, all of it multiplied by dP, to be equal to the indefinite integral of k times dt. Now we can start integrating a little bit, and we're going to take the integration of 1 over p, which will be the natural log of p. The next one will give me the natural log of L minus P. And here we're going to get KT plus the constant of integration. Now at this point here, there's going to be something that a lot of students are not necessarily going to see on their own. Okay, so at this point here, what I'm looking at specifically is what's inside of this absolute value, or parentheses, or however you have it written. Here, let me just write this over here on the side. The derivative of that expression, L minus P, where P is the variable. P is like the X value or the Y value or whatever that we would take the derivative with respect to. The derivative of L minus P in this case is just negative 1. Okay? So because the derivative of that is going to be a negative 1, you need to add a negative sign in front of that natural log. Okay? So that means I'm going to end up here with natural log of p minus natural log of L minus P to be equal to KT plus C. Now, at this point here, based on what I know about properties of logarithms, we can take the expression on the left side, the two logarithms, and we can write them as one logarithm. But if I do, I'm going to wind up with P over an L minus a P. And working, just thinking my way through the rest of the problem at that point, I would prefer the L minus P expression to be on top rather than the P expression to be on top if I used my log properties to condense those into one expression. So in order to accomplish that, what I'm going to do, I'm going to multiply the entire equation by a negative 1. Okay? So multiplying the entire equation by a negative 1 will give me a positive natural log of L minus P minus the natural log of P to be equal to negative KT. And we kind of, and if you go back and look at the general solution, if you notice, does have a negative sign on the K value. So this is kind of why and where the negative sign is being applied to that K value. So minus C. And now we'll go ahead and condense our logarithms. So I'll have natural log of L minus P over L. Nope, over P. I don't know where my head is right now. I keep writing the same, wanting to say things, and I write the wrong thing, or vice versa. Over P equals negative KT minus C. Now the reason why we want to condense it is so that now we can exponentiate the function and get the p variable out of the logarithms, parentheses or brackets or absolute value, however you're thinking of it. So I'm going to wind up with the L minus P over P to be equal to e to the negative KT minus C power. Well, on the right side of the equal sign, we can use some exponent properties, and I'm going to say L minus P over P is equal to E times to the negative KT power times E to the negative C power. We're just understanding that powers at the same base, we're adding the exponents, so I'm just kind of going backwards or opposite of that. And the idea of doing that is to illustrate this right here. This part right here is just a constant. Well, that constant in our general solution is represented by the letter A. So that's where the A comes from. It doesn't matter that the exponent is negative. It's just going to be a constant value. Okay? So this now puts me at L minus P over P to be equal to A times E to the negative KT power. So we're almost there. Almost there. We got to get P by itself, however. So I'm going to multiply by P to get the P out of the denominator. I'm going to say L minus P will be equal to P times A times E to the negative KT power. KT power. Ugh. Erase. Write it a little bit neatly. kt power. And then we can move the p from the left side to the right side through addition, and that'll give me L to be equal to p plus p times a times e to the negative kt power. Factoring out the p and then dividing, I'll get p times 1 plus a times e to the negative kt power, and you can see how it's all coming together now. So we wind up with L over p, nope, 1 plus a times e to the negative kt power to be equal to p of time, or p of t. And that's how we go from the general solution, or I'm sorry, from the differential equation to the general solution of the function. Okay? Are we having fun yet? Is that fun concepts here? Now, this side note that are in the notes tells us that the parameter L, the limiting factor, or the carrying capacity, represents a limiting value. The parameter K represents the relative growth rate when P is small relative to L. And so the parameter A depends on the initial value, P naught. And so we can, in this case, for logistic functions, we can identify the value of A, that initial kind of value in the overall general solution, to be the limiting factor minus P naught divided by P naught. Now, personally, I don't need to feel like the need to encourage you to remember that. If you do and it's useful to you, then go for it. But it's a fairly niche application of something. There's a general way that we can find A for a lot of problems that are going to have these e to the kt power things that I think are going to be more broadly and therefore more likely to be remembered by somebody that needs to work with it. So the carrying capacity in this case, and if we, let me just go ahead and write out the general function. So or not the general function, but the differential equation. So here we have dp dt was equal to kp times, what was it, 1 minus p over L. Okay. So you can see as p approaches 0, let's say we have a 0 over L. Well, 0 over L is 0, right? So 1 minus 0 is 0, and 1 minus 0 is 1, and 1 times kp is just kp. So as p, whatever that is, whatever that represents, approaches 0, then the solution of the differential equation, dp dt, is just going to approach whatever the value of k times p happens to be. Now, if we look at it again in terms of, now instead of saying p approaches 0, now let's say what happens as p approaches L. Well, that's going to give me L over L, which would be 1. 1 minus 1 in the parentheses becomes 0. 0 times k times p is just 0. So as you approach your limiting factor, whatever that happens to be, your carrying capacity, your slope, your solution of your differential equation approaches 0. And when we look at it on a slope field, it is going to make sense here. So here is just a general logistic curve graph. Okay. I don't remember what it's telling you here on number 3. The graph of the function p. Okay, there's our logistic curve. In logistic growth, the population grows fastest when the population is half the carrying capacity, and that's what I'm saying right here. The maximum value of dp dt, the time when the slope is the greatest value, is when the population, or whatever it is half of the carrying capacity. And I have a typo here. This is not a logistic curve. This is a logarithmic logarithmic curve. But that's essentially what a logistic growth function is. You see to the left of the maximum slope, that point that's been identified for you where the point of inflection is. The left side of that is an exponential growth function, and the right side of it is going to be more of a logistic growth function. Okay, the dotted horizontal line up at the top would represent the carrying capacity, and you can see, based on what we just talked about a moment ago, is as P approaches L, I'm sorry, as P approaches L, you can see that the slope is approaching 0. And as P approaches 0, then the way that we would find the slope is we would just multiply the relative growth rate, K, times whatever P happened to be at that point. Okay, so let's move on here. The slopes the slopes are small. Looking at the slopes, coming back here, where are the slopes small? Well, the slopes are small, kind of around the carrying capacity. You can see around the carrying capacity, around here, we generally have slopes that are small, not so much, at p is equal to 0, but we're also going to have relative slopes that are small whenever p is kind of going towards 0, kind of like that. So what we're looking at here, the slopes are small near when p is equal to 0 and when p is equal to the carrying capacity as they approach. It's steepest around the point of inflection, which was when we said half of the carrying capacity. And what happens if P is greater than L? I don't remember if I had anything here. I don't think I do. What happens if P is greater than L? If the population is greater than the carrying capacity, the slopes that we would see of our differential equation would be negative. Meaning that the population, whatever it is, population decreases. Okay, so here's where the rubber meets the road, so to speak. So we've talked about what a logistic growth function is, established how we took the general differential equation for it to create a general solution, and then now we're going to be looking at it in terms of an application. And this application it's one essential question, but it's going to kind of have multiple parts to it. You will probably benefit from having a calculator. In fact, at some point, you may want to graph the differential function on your calculator just to see for yourself what it's going to give you. Okay. Now, what it's asking, it gives us a situation, a population of coyotes in a preserve is modeled by a logistic function. Makes sense. In real world, we can't have unlimited growth. The preserve can support no more than 100 coyotes on the property. Well, if it can support no more than 100 coyotes on the property, that 100, that tells me that's the carrying capacity. So in this case, it's asking us to write a differential equation where K, the relative growth rate, is 0.1 and time is going to be measured in years. So there's a couple ways that we could write it. Using the equation as it was kind of given to you, you can say dp dt would be equal to K. Let's just go ahead and write the general one. K times P times 1 minus P over L. Substituting, we would get 0.1 for k times p, and then in parentheses we would just say 1 minus p over L in this case, which would be 100. And we could, you know, say that that's what we have. One extra thing that we're going to do, and I'm going to do this because I'm going to use it to make a point later on. We can also distribute that into the 0.1p into the parentheses and get 0.1p minus 0.001p squared, and then we can factor that to be 0.001p times 100 minus p. We could also write the differential equation like that. And the way that I have it written at the bottom is going to be something I'm going to refer back to at some point to try to simplify things for you. Okay, there's going to be a problem that I'm going to work out. It's going to be a little bit lengthy, and I'm going to show you the long way first, and I'm going to try and show you a shortcut depending on what your applications are going to be to try and help you out. So don't hate me that it's going to be long, but there's a reason why I'm doing that at the bottom. Okay? So what it says, and I don't know why the graph is being put here. I don't know why the slope field is given to us here. But B, the slope field is shown below. Okay, where does the horizontal asymptote appear to occur? So that makes sense while we're looking at the graph here. Well, the horizontal asymptote is kind of, let me get a brighter color here. The horizontal asymptote, looking at the graph, we have positive slopes pretty much everywhere. We might have a horizontal asymptote down here at 0, but that's not where our carrying capacity is going to be. In fact, they told us what our carrying capacity was going to be was 100. So right at 100 is where my slope of 0 should be. And I know I didn't draw that line very well, but that one should be at about when p is equal to 100. Well, what happens if the initial population is above the asymptote? So if the population is kind of up here, well, that means that there's probably too many wolves for the region. Okay, if there's only enough like game or whatever, or even land for the that's been fenced off or partitioned off in some way for these wolves to live there, uh, the number of like say you just magically produced a whole bunch of wolves, more than 100. Well, what's going to happen is that wolves are going to start dying off in such a way so that way they can come down to that carrying capacity. So in this case, they would be there that if the initial population is above the horizontal asymptote, it means that the region is overpopulated, and that way, you know, there's going to be scarcity for food, and ultimately, you know, wolves are going to have to die off. So that way, you could maintain a healthy population, even if it is at the upper limits of what the healthy population could be sustained at. Okay. So here, part D, if the preserve initially begins with 20 coyotes, okay? So there's the key word, and initially, if it initially begins with 20 coyotes, okay, so at P of 0 or P naught, we have 20 coyotes, or when time is equal to 0, we have 20 coyotes. So it's asking us to sketch a graph on the slope field. Okay, well, this isn't going to be something that we're doing to try and get perfect here or anything. The initial point at time is equal to 0. It's going to be 20. And based on what we know, or what I showed you earlier on what an logistic growth function looks like, is it's going to kind of look exponential to begin with. You know, so we might be kind of coming this way. I know technically we're not going to be on the left side of the x-axis because negative time and whatnot, but you know, it's going to do one of these things where it's going to grow exponentially. Excuse me, and at some point it's going to grow, and I think I'm not growing it enough here. it's going to grow and grow and grow, and at some point following those slopes, it's going to get to that horizontal asymptote and say, okay, we're done. That's all the wolves you can have at this party now, so we're done. So part E, find the general solution and the particular solution. Now in this case, the general and the particular solution are basically going to be the same thing, okay? Because it's telling us the particular solution at the initial conditions. And this is where, guys, don't hate me, I'm going to give a little bit of work, and I want to make sure that you understand why I'm doing it. So the first way that I'm going to do it is very similar to what I did at the very beginning in that first example, where we did all the calculus with the separation of the differential equation, so that way we could identify the general solution of the differential equation, where we had to do the separation by, or the partial fractions and all that stuff. So we're going to do that here first. And partly I'm doing that because I don't know what kind of application you're going to be asked to do this with. And I have always been trained that a free response question needs to have calculus justifications only. So if you have a question like this as a free response question on an AP exam, do you need to do all this calculus? Maybe, I don't know. And I don't want to cheat anybody out of the experience in case that's what you need. So find the general solution and the particular solution. So we are going to need some space to do the work. And on this one, on the notes, they're actually giving you a fair amount of space to work it out. So based on what we have for our initial population, we're going to say that in this case, dp dt will be equal to the k value, which was 0.1 times p. In parentheses, we're going to say 1 minus p over 100. So when we do our separation of variables, multiplied by the reciprocals of the p terms, and I'm going to get 1 over p times 1 minus p over 100 dp to be equal to 0.1 times dt. And at this point, this is where once we have the variables separated, we take the integration of both sides. And just like what I did on the first one, I'm really going to focus on the left side first because that's where a majority of the work is going to come from. So I am going to learn from what I did the first time and recognize that I want to kind of simplify the stuff that's in parentheses. So I'm going to multiply by 100 on both parts of the fraction, okay? And that will give me 100 over p times 100 minus p dp. Well, no, we're not doing dp here. We're going to do our separation with our partial fractions. So this is going to be a over p plus b over 100 minus p. And again, we're going to find out what the values of a and b are. Now, I'm not going to do the work, to find the values of a and b. Just understand, there are other lessons that I've made that you can go back and review, go even rewind and go back to the beginning of the lesson here and see what I did there. And in this case, a is going to work out to be a 1, and so is b. B is also going to work out to be a 1. Okay, so at this point, coming back to the overall problem, we can rewrite the left side with the indefinite integral of 1 over p plus 1 over 100 minus p dp to be equal to the indefinite integral of 0.1 dt. Now we can find the antiderivatives of each one. So the antiderivative of 1 over p is going to be the natural log of p. And again, what we're going to want to do is we're going to say plus here, but again, when I take the derivative of the denominator, because if I write it out as the natural log of 100 minus p, the derivative of that part here is going to be a negative p, so this part here needs to be negative. So we're going to just write it out as minus natural log of 100 minus p to be equal to 0.1 t plus the constant of integration. And again, at this point, what I'm going to do, similar to what I did on the first one of these that we worked out, I can foresee what's going to happen with the logarithms. We have to condense them. And again, I want the larger term on top, so I'm going to just multiply everything by a -1, so that way I can ensure that's going to happen. And I'm going to have the natural log of 100 minus p minus, I keep wanting to say plus, minus the natural log of p to be equal to negative zero point 0.1 t minus c. And now we can see that we can condense the two logarithms into one, and that'll give me natural log of 100 minus p over p to be equal to negative 0.1 times t minus c. Exponentiate both sides, and I get 100 minus p over p to be equal to e to the negative 0.1 t minus c power. And we've already seen how that is going to simplify. We're going to wind up with that to be on the right side 100 minus p over p to be equal to a times e to the negative 0.1 t power. Move the p's over, and in this case, I'm going to wind up with 100 minus p equals, let's just go ahead and move that p over now, I guess. Save myself an operation here. So 100 will be equal to p plus p times a times e to the negative 0.1 t power. And factor out the p and divide by the remaining terms, and I'm going to be left with 100 over 1 plus a times e to the negative 0.1 t power to be equal to p of t. So that is essentially what we might think of as the general solution, okay, because we have our constant of integration still here. In this case, we're calling it an a instead of a c. So if I want to identify what the specific constant of integration is, you can find the a value by, let's go back a little bit. You can find the a value by using that little rule that they gave you. Golly, I didn't realize it was so far back. You can find the a value by looking at this, okay? Personally, I don't like doing it that way simply because I just, it's too niche for me, I think. So what I'm going to do here is I'm going to find a the way I would typically find a, okay? So I know I'm kind of at the bottom here, so I'm going to just kind of rewrite it up here at the top, okay? So up here at the top where I have a little bit more space, we were at 100 over 1 plus a times e to the negative 0.1 t power to be equal to p of t. Okay, well, we can evaluate this pretty easily at p of 0 when time is equal to 0. This is essentially what we're going to be evaluating it with to identify your a value. Okay, so if I substitute 0 for time, we're going to get 100 over 1 plus a times e to the 0 power equals, and in this case, P of 0 was 20 wolves. That was the initial population. Okay, so cross multiplying, and we're going to wind up with 5 to be equal to 1 plus a, and so now you can move the 1 over and say a in this case is 4. Oops, don't need to write 4 twice. So now I can take that and say that my specific solution, P of t, would be equal to 100 wolves, or that's the carrying capacity, divided by 1 plus 4 times e to the negative 0.1 t power. Okay, that is the specific solution. And all of it was figured out using a calculus approach. Now, is it necessary to use a calculus approach here? No, it is not. And so now let me show you a different way of doing it. So again, apologies for, I'm not trying to punish you, just trying to be, thorough and make sure that if you need to do it with calculus, you have the calculus methods at your disposal. Now, one thing that I want to point out to you guys here, and if you're looking at this for class purposes, this is definitely going to help you on your homework assignment. One of the things I want to make sure that you understand is that the k value of the differential equation and the k value of the general solution they may not always be the same. Now, in this example, the way that I just worked it out, the original problem told us that k was equal to a positive 0.1. That was the k value of our differential equation. And the k value of our general solution worked out to be a negative 0.1. Now, in this case, the sign is the only thing that's different. But the k value of the general solution and the k value of the differential equation are not necessarily going to be the same overall value. They're not even going to be the same absolute value like they were in this example. So what we can look at here, and I'm going to show you that in a moment. We're going to come back to this. Okay. But now let's shorten things up a little bit. So what are we being asked to do here? Specifically, we need to identify what is the particular solution of the differential the differential equation. Well, if you know what the general solution is, you can say that, well, let's start there. P of t is supposed to be equal to L over 1 plus a times e to the negative kt power, negative kt power. Can you figure out what those things are going to be? Sure you can. Okay, the way that I just showed you to find the a value on that at the tail end of that very long calculus method is the same way that I would do it here. Again, I'm going to say, okay, well, at time is equal to 0, how am I going to get the a value? Well, at time is equal to 0, the initial population was still 20 wolves, and we work it out literally the exact same way. We would say, in this case, 100 for the carrying capacity over 1 plus a times e to the 0 power when I substitute 0 for time. And so we're going to wind up with cross multiplying 1 plus a to be equal to 5. Subtract the 1 and we get a 4 for a. Great, we got 2 of the variables that we need. Okay, well, how do I find k? So this is how I'm going to find k. K of the general solution is going to be equal to the k value of the differential, let me make that capital, so it's of the differential equation times, and in this case, it's going to be times the carrying capacity. Now, if you recall, earlier, what I did is I took the differential equation, and I wrote the differential equation by distributing it and then factoring it. And I said, going back to, I believe, part A of this example, I said that dp dt was equal to 0.001 times p, and in parentheses, we had 100 minus p, okay? Well, the k value of the differential equation that I'm looking at, in order for this little shortcut to work, so let me get something not quite so big. The k value that I'm looking at here for the differential equation is this 0.01, not the 0.1 that was given to me in the problem. So if I take if I want to know the k value of the general solution, I'm going to take the k value of the differential equation, 0.001, can't write my zeros right apparently, 0.001, and I'm going to multiply it by the limiting or the carrying capacity of 100, and that's how I'm getting 0.1. Not because that was what was given to me in the problem originally, because again, the general growth factor of the general solution and the differential equation, those two k values are not necessarily going to be the same thing. So what I'm going to do is I'm going to take that 0.1 and I'm going to just stick it in here where the negative sign is already given to me, and now I know my a value, so I'm going to take that and put it in here. And so now I can say P of t is equal to my carrying capacity over 1 plus 4 times e to the negative 0.1 t power. Was that shorter? Was that easier? Did it require a lot less work? Yes. Did I use any calculus? No. Okay. So 6 of one, half dozen of the other. Take your pick, which one you want to do. Understand that maybe if it's a free response question that you're working with, maybe you have to use calculus in order to get credit for it. Because free response questions, calculus justifications only, that's all they really care about. I can't say with any certainty that if you did this on a free response question, a test grader is going to give you credit for it. So I just want to be clear on that. Okay. But either way, we found the general solution. Now part E, part F and part G and part H, the remaining parts that follow up with this, they're relatively straightforward. There's not really any work to do with them. Okay, when will the population reach 80? So here we're solving for time, so we're going to take the general solution that we had, which was P of t was equal to 100 over 1 plus 4 times e to the negative 0.1 t power, and basically we're going to solve this for time when the population was 80. So here this will be 80 equals 100 over 1 plus 4 times the e to the negative 0.1 t power. Again, cross multiply, and we're going to end up with 1 plus 4e negative 0.1 t to be equal to, let's see, 100 over 80 is going to be 1.25 as a decimal. Move the 1 over through subtracting, and I'll get 4e to the negative 1.1 t equals 0.25, and then I divide that by 4, and that'll give me e to the negative 0.1 t power to be equal to 0.0625, and now this is where we have to exponentiate again using your log loop. So in this case, we're going to wind up with, essentially you take the natural log of both sides, and we're going to get negative 0.1 t to be equal to the natural log of 0.0625, and divide that by negative 0.1, and you'll get time to be approximately equal to 27.726 years. So there's that one. Part G, following for the next step. Oops, did I miss it? Is it further down that page? It sure is. When is the coyote population growing the fastest? Well, it's growing the fastest when it's half of the carrying capacity. So the population is growing fastest when at the half of the carrying capacity, which would be 50 in this case. So here, no, not P of 50. P when P of t is equal to 50. So we would, basically repeat the whole process that we just did a second ago, and I'm going to end up with 1 plus 4 times e to the negative 0.1 t power to be equal to 2. And then working it out, we're going to get negative 0.1 t will be equal to the natural log of 0.25 dividing by t. In this case, will give me about 13.863 years. And find the limit as t approaches infinity of the function. Well, we've already established that as you approach infinity, or as p gets very large, or as in this case time gets very large, we're going to approach the horizontal asymptote. So the limit of this one in this case is the carrying capacity 100. Now at this point here, before we move on, I want to go back to the calculator. So we've already seen a sketch, and this is something that I want to just talk with you guys about. So give me 1 second. Okay, so here we're looking at the calculator, and what I want to do is because we had a sketch earlier, and it was just a rough sketch of what the solution curve should look like. But there may be a time when you need to do the same thing and actually graph the differential equation. So this one I found to be a little bit interesting. So I'm going to go to menu, and we're going to look for our differential equations, and we come here. Now, the general solution or the differential equation that we had was 0.1, and in this case, P is going to represent Y on the calculator. So I'm going to say Y1 on the calculator. So that's P. And then we had in parentheses 1 minus P over 100. So I'll say Y1 again over 100. Now, if I just try to graph this by itself, I'm continually getting this thing here that says an invalid math expression. And for the life of me, I couldn't figure out why it was doing it. And I played around with it and played around with it after I threatened to destroy my computer out of frustration. And ultimately, I just said, well, what if I just tried doing it with the factored form? And if I said 0.1 of y1 minus 0.001 of that same function, but we have to square it. If I graph that, then I wind up with, a slope field that would work. So now, and I don't understand the difference. I don't know why it is doing that. So let's go back to here, and we know our initial conditions. When time was 0, we had 20 wolves. And if I come here to these dots, we could see what the step size is if we wanted to. And in this case, looking at the graph that was originally given to you, they're doing it in terms of years, I believe. So in this case, delta x would be, I don't know, 5. Kind of a big step size here, but we can say 5. We can increase the resolution if we want to, and try graphing it now. And it's not giving us the solution curve for some reason. Oh, it's because it's not, the window settings aren't where I can see it. Where's my... Let's try setting the window. Let's just see if we can put our own window settings here. So if we go 0 to how many years did it kind of go out? Say 50. And the y value we knew, we'll just start it at 0 for our population size, and our carrying capacity was 100, so let's just say 110. And let's see if we see anything. And I get something over here, but I'm not really seeing, well, but at least we're able to get a slope field. I don't know why why the general curve here isn't being shown up. But again, I make no bones about the fact that I am still a novice at the Inspire calculator because I've never been forced to use it. Okay, there we go. Now we can see it, put it back with the initial values there, and there we go. And we can kind of see that where it is. Here's what the Euler method would show as our approximate value. And again, if we wanted to, we could take the general solution and graph it alongside with to see how they actually compare. But I just wanted to kind of point that out, that if you did want to graph this particular differential equation, and it may just be me that doesn't understand what I'm doing, if I just type the differential equation as it was, I wasn't able to get it to show up. I kept getting that error message, invalid math expression. So maybe somebody out there knows more than I do about it and can give a much better. So here, if we needed to, we could take the points from our graph and say, okay, yeah, that's about what it's supposed to look like. Okay, so that is the logistic growth function. That was the third of the 4 differential equations that a BC calculus is responsible for knowing. And so the fourth one that we're going to be taking a look at is going to be this one, Newton's law of cooling. Now, Newton's law of cooling may have been something that you got exposure to in a pre-calculus class. I remember when I taught pre-cal, this was something that was included in an exponential and logarithmic unit of study. Newton's law of cooling is essentially going to be able to show you the difference between an object's temperature and a fixed constant. Typically, it's going to be the temperature of the room that you're in. It doesn't necessarily have to be, if you were doing something underwater, it would be this temperature of the surrounding body of water. But for us, generally speaking, it's going to be the temperature of, like, the ambient temperature of a room that you're in. So the general, or the differential equation that we have, dy dt, is going to be equal to the k value, and again, that's a relative growth rate, times y minus b, and b, in that case, the b is going to be the constant. That's the ambient air temperature, or whatever it is of the room that you're working with. And the general solution is going to be a, again, that would represent the constant of integration. Constant of integration as we work through the problem, a times e to the kt power plus b. And again, they're kind of giving you this niche little thing here to show you that a can be found by taking the initial temperature, or whatever you have, minus the ambient temperature to get the a value. Okay. So in this case, we're going to be looking specifically at Newton's law of cooling, but there is a law of heating as well. Uh, so let's go ahead and work with what we have here. This one is going to rely on a lot of kind of algebra skills that you had, kind of like what those last couple of problems on the logistic growth examples did. You bought your favorite frozen coffee treat on the way to school at the drive-through of Starbeams. And let's avoid a lawsuit here. Your car is always kept at a constant 65 degrees, so that's important information. So that constant 65 degrees, that is going to be that constant temperature, the B value. Traffic was terrible. You spent 10 minutes getting to school. The drink warmed to 35 degrees. So here we have a time value and a temperature value associated with it. So these two things are going to go together. Time value and temperature value of 35 degrees. Because you checked it with your temperature probe at the red light, because who doesn't have one of those in their car? Want to see how well the windows insulate the inside of the car from the outside of the car. Then two students had a rear end collision and another 10 minutes passed. So we have another time interval here, 10 minutes passed to get into the parking lot, and you checked your temperature again, and your drink had warmed to 50 degrees. Use Newton's law of cooling to estimate the following. What was the frozen coffee's original temperature? Okay. So this is very much kind of a word problem. A lot of people don't like word problems. They just want to say, here's a problem, differentiate it, solve it, whatever the case is. But here with word problems, we have to be able to think our way through what we're looking at. Now in this case, there's really not much in the way of calculus, much if anything in the way of calculus that I can recall when I worked this problem out before. Well, let's see what we know. Okay, the general solution of Newton's law of cooling is A times e to the kt power plus b. And let's see, do we know A? Not really. We don't know an initial temperature that we started off at. Do I know the relative growth rate? It was not apparent in the problem to me. Do I know the constant temperature, B? I do. That was 65 degrees Fahrenheit. So if we're going to try to use the general solution, and again, maybe you have to go through all of the solving of the differential equation like I did on that one really long example before I kind of showed you how you could cheat a little bit and use a shortcut. Maybe you have to do that. I'm not going to do it here. I'm going to just figure it out what the problems are going to be. I can't foresee much of Newton's law of cooling being a huge deal for anybody. But if I'm wrong, feel free to give me an I told you so. You were wrong, Mr. Piercy. So we have to be able to figure out what the values of A and K are going to be. We got to be able to figure out the constant growth rate, and we have to be able to figure out A. So what do we know? Based on the information that was given to us, we know that at y of 10 minutes after you got your coffee, that the temperature was 35 degrees Fahrenheit. So that could give us an equation of 35 to be equal to a e to the 10k power plus 65. We also know that 10 minutes after that, at y of 20, that the temperature had risen to 50 degrees. So we can show that 50 is equal to a times e to the 20k power, or 20t power plus 65. And with those two equations, we can compare them because we're comparing like to like as far as time, the constant value, things like that. We can kind of look at these and compare them. So let's move the 65 over on both of them. So if I move the 65 over on the one on the right, I'm going to get negative 15 equals a e to the 20t power. And if I look at the one on the left, move the 65 over, that's going to become negative 30 equals a e to the 10k power. So what I'm going to do with this stuff here, it looks like I can kind of take this and this. I'm not going to treat it like a standard system of equations, but I can definitely compare them and be able to figure out, I can use this information to figure out the value of k, okay, without having really to do any calculus. So if I take the negative 30 equals AE to the 20, nope, that one's 10, to the 10t power, and I divide it by the negative 15 equaling A to the times E to the 20k power. When we simplify this overall ratio, we're going to get a positive 2 to be equal to E to the negative 10t power. And this is where I can exponentiate to find the value of t. So here I'm going to wind up with the natural log of 2 to be equal to negative 10t. So divide the natural log of 2 by negative 10. And I don't remember what the number was. I just know it's not a very nice number from what I remember. I'm going to just leave it in the exact form. It'll be the overall negative natural log of 2 over 10 to be equal to, nope, why am I saying, why am I writing, I did that on all of them, on a whole bunch of them. That's k. K, I wrote k there, k, k. This is the k value that we're finding. Sorry about that. So now that we have a value for k, let's find a. Okay, and I can do that using either of the two equations that I have. But let's find a. So in this case, if I wanted to find a, I'm going to kind of look at this one here because just because I could do the same. I could do it on the other one. If I wanted to find a, I'm going to say negative 30 is going to be divided by e to the 10k power to be equal to a. Well, we know what k is in this case. It's going to be the natural log of 2 over 10, or I'm sorry, yeah, natural log of 2 over 10. So we're going to say negative 30 e to the 10 times natural log of 2 over 10, 10, I don't know why I wrote a 2, equals a. And you can kind of see where this is going to go. The tens are going to wind up simplifying. If you wanted to, you could, just type that into your calculator as you see it. You can simplify it using properties of logarithms, but in this case, negative 60 is going to be equal to the a value. So now we have our relative growth rate k. We have the value of the constant of integration for this specific problem to be 60. Okay, so our specific solution in this case is going to be y, or p of t, or temperature, whatever you want. I'll just leave it as y. Y is equal to negative 60 e to the, let's see, k power, negative natural log of 2 over 10 times T power plus the ambient temperature of the car, 65 degrees. Now what we're being asked to identify is what is the car's initial temperature. Not the car, the coffee's initial temperature. So at time 0, what's the initial temperature? So in this case, well, let's say T of 0, temperature at time 0, would be equal to negative 60 e to the 0 power effectively, plus 65. So negative 60 times 1 is negative 60, plus 5 is 5 degrees Fahrenheit. So, brain freeze city, here we come. Well, the follow-up questions related to this, when did the drink reach a specific temperature of 63 degrees? So here we're going to solve the function in terms of time, okay? Now to simplify things on this one, I'm not gonna write the natural log of negative natural log of 2 over 10 each time. I'm gonna just write it as k until I'm ready to actually divide with it or something. So we know in this case again, our general solution, or our specific solution I should say, was negative 60 e to the kt power plus 65. And again, we know that k is equal to negative natural log of 2 over 10. I'm just not going to write it every time. So in this case, we're looking to see when it's going to reach a temperature of 63 degrees. So the temperature will be 63 equals negative 60 e kt plus 65. Move the 65 over. Negative 2, negative 60 e kt, divide. Negative over negative gives me 1/30 equals e kt power. So that'll be natural log of 1/30 equals kt. So now I divide by the k value. So we're going to wind up with like the natural log of 1 over 30 divided by negative natural log of 2 over 10. And you can multiply by the reciprocal of that if it makes it a little bit easier, or just type it into your calculator. But in this case, that'll give you the time, and if you work that out, here time will approximately be equal to 49.069 minutes. And the final problem, what would the temperature be of the drink be after 1 hour? The one thing that you really kind of need to pay attention to on this one is they told you the problem at the beginning, told you that time was measured in minutes, and here they're giving you time in hours. So straight away, you want to make sure that you recognize, in this case, we want to use 60 minutes for the hour, because that's what our function was worked out to be with in terms of time. So this one's going to be somewhat of a plug and chug exercise. You're not going to really need to do a whole lot of stuff here. So we're going to be looking for temperature after 60 minutes to be equal to negative 60 e to the negative natural log of 2 over 10 times 60 plus 65. And we can simplify that if we really wanted to, or we could just type it into our calculator. If I really feel like simplifying it here, okay, this just looks to be e negative 6 natural log 2, which would be e natural log 2 to the negative 6 power. So those are going to cancel each other out, leaving me 2 to the negative 6, which is 1/64. But either way, you type it into your calculator, negative 60 times 1/64 plus 65, whichever one you do, this one or this one, when you type it into your calculator, t of 60 is approximately going to be 64.0625 minutes. And that's going to wrap it up for the lesson on logistic growth and Newton's law of cooling. And again, I know that the video length is a little bit long, but hopefully it was detailed and gave enough explanation about why I'm doing certain things the way that I'm doing them, and to understand that in some cases, if you are working on a problem thinking that you're doing it correctly, you may very well be, but you may need to go back and try and simplify things and then restart it again. Do I have to do calculus 100% of the time? No, not really. Maybe you need to for a justification on a free response question. I would, I'm going to look into that and maybe try to get a little bit more feedback on it. But that hopefully is going to wrap things up and clear things up for you about what the final two differential equations you're going to need to be responsible for on your AP exams. And until next time, guys, thanks for watching. Take care and be good.